This video is summarising and reviewing the topic of momentum, which for Year 13 is in the Newtonian World module, and for Year 12, for the new specification, is part of Module 3, which is forces and motion. So, momentum is a quantity we always talk about when we are dealing with collisions. So, the first thing that you need to understand is the principle of conservation of momentum, which basically states that the momentum before a collision must equal the momentum after the collision. Now, this statement on its own, momentum before equals momentum after, isn't sufficient for anything. So there's a couple of words that we've got to add, right? So the first thing is the total momentum before. So if I put the symbol for sum, so the sum of all of the momentums before a collision and the sum of all the momentums after a collision must be equal to each other. Okay, so the principle of conservation of momentum, you must say that the total momentum is conserved, and the other condition is that it is for a closed system. Now, what this means is that there are no external forces when the conservation of momentum applies. So you must remember it is for a closed system, and we're going to try and demonstrate this. Now, you need to remember the equations for momentum. So the first basic equation we have for momentum is mass times velocity, and this is instantaneous momentum of an object. I can then adapt that to give me change in momentum is mass times change in velocity, because obviously the mass itself can't change, or at least it usually doesn't. And that I can expand that to say that mv minus mu is equal to a change in momentum, or I can write it another way, which is mv minus u. Now, all three versions of those equations are useful for working out calculations, so it's important that you understand them. Now, the other thing that we have for change in momentum during collision is that because of Newton's second law, which is that force is proportional to the rate of change of momentum, if we rearrange this equation, we get change in momentum is equal to force times the duration of a collision, which is the change in time. Now, this quantity here we call impulse. So when we define impulse, we do it as force multiplied by the change, force multiplied by the duration of the collision. Now, that also comes if you have a force time graph. So if it's a momentum question, you will most probably have a force time graph, and for a collision, you will have a collision, possibly like so, and the area under the graph here, this is delta rho, which is the impulse. Now that means that I can make this area under the graph. So if I work out the area under the graph, now if I was doing it for a shape like this, what I would have to do is either split it into two triangles and then halve it as an estimate. I could count the squares, or I could do an approximation and say, well, turn it into like a rectangle and use that. Any of those methods for working out the area under the graph would give me my impulse. But what we then say is that the change in momentum, which is my impulse, we've worked that out by doing F delta t. That is equal, we can say over here, to the mass of the object times the change in velocity. So if I know the initial velocity is 0, for example, I can work out the final velocity. So recognizing that these two things are equal is really important. Now, if we go back to the conservation of momentum and link it to these force time graphs, if I have a force time graph for an object A colliding with object B, so if I simplify this and make it very simple, I initially have no force until the collision occurs, and then at this point I will have a force of relatively constant magnitude, to keep it very simple, applied on an object, and then obviously once the collision's over it stops. So we know this area here is the impulse, okay? This is the change in momentum for object A. Now, because of Newton's third law, which states that if object A exerts a force on object B exerts a force that is equal in magnitude, opposite in direction, and of the same type. So this bit here would be the change of momentum for object B. And we can see that whenever we have any collision, the change in momentum for one object must be equal to the change in momentum for the other object. But obviously it's the minus, so it's in the opposite direction. Now, this can also be linked to if we were commenting on, okay, what's the impulse between two objects? Well, this demonstrates that. So the impulse on each of these objects is equal but opposite, which you can see by this expression here, because the force is equal and opposite, and the duration of the collision is the same for both. So if the force is the same but opposite, and the duration of the collision is the same for both, the impulse must be the same for both objects. So this relationship is important. Now, if we look at situations where we have collisions, then there are three possibilities that we could have. So the first is that I have two objects that are going to collide with each other, m1, which will have its initial velocity, and m2, which will have its initial velocity, and they will collide with each other and then bounce off. So the final momentum will be m1v1 plus m2v2. Now, I can have a situation where instead of the two objects rebounding off each other, they stick together. So in that case, I'm going to have m1u1 plus m2u2 is going to be equal to m1 plus 2, so those two added together, the masses, v, which is the final speed. And equally, I can have this situation backwards, where I have an object that's exploding. So m1 plus 2 u is equal to m1 v1 plus m2 v2. So those are the only three situations I can have in terms of collisions. So if I understand all of these equations here and can use them freely, I can answer pretty much every momentum question I'm ever going to get. Now we're going to look at one specific example, which is which you've been given as a worksheet before. So in this situation, I have a container. Now, the container is in space, and inside the container there is a box, okay, which is split into two halves, A and B. Okay, now the box is 0.4 meters wide, and I know my diagram is not perfect, but we say that it is from this point to this point is 2.1 meters, and I know my diagram doesn't match this, but this side to here is 3 meters. Okay, so it's further to this side. Okay, and we've got this container, and what's going to happen is these objects are going to explode. So the equation that we know we're going to use is this one. This one. Okay, this equation that I've written here. So this equation relates to this situation below, but we just changed the 1's and 2's to A and B. So let's add the information that we know about this. So the container overall has the mass of the container, which I'm going to use as C, is equal to 45 kilograms. Okay. The total length, which you can probably work out, is 5.5 meters. And the total mass of this cube, so the mass of A plus B, is equal to 15 kilograms. Okay, now it explodes into two pieces. Mass A, so MA, is 5 kilograms, and mass B is 10 kilograms. Okay, and they're going to explode, and they're each going to have velocity. So A is going to have velocity VA, and B is going to have velocity VB. Okay, and this explosion occurs at t equals 0, so our starting time. Now, the explosion gives A momentum, so the momentum of A is 10 kilograms meters per second. From this, we can then calculate the speeds VA and VB. So momentum of A is equal to the mass of A and the speed of A. So I rearrange this to give momentum of A over the mass of A is equal to the velocity of A. So I have 10 divided by 5, and so the velocity is 2 meters per second for VA. So VA is 2 meters per second. Now I'm going to make that positive. So I'm going to make that my positive direction, just to keep this consistent. Then I can do my VB, which has to have, if momentum of A is 10, I'm trying to work out VB, that must be the momentum of B divided by the mass of B, but the momentum of B has to be equal to minus 10, because remember it's a vector, so if that's 10 in that direction, the change in momentum we said for any two objects in a collision has to be the same. So since the mass of B is 10, it's 10 divided by 10, which is equal to 1 meter per second. So VB is minus 1 meter per second, because it's minus 1 divided by 10. Okay, so we have our speeds. Next, we're asked to consider what the time t1 is. Now, t1 corresponds to the time A is going to collide with B. So we know its speed, and we know the distance it's travelling. So this is very simple now. So the velocity is equal to displacement divided by time, and this is time t1. So t1 is equal to velocity of A times, rearrange that, displacement divided by velocity of A, which is equal to 3 meters divided by 2, which is equal to 1.5 seconds. So t1 is 1.5 seconds. Now what I want to calculate is how far left. So you imagine a couple of seconds later, B still hasn't hit this wall of this container because it's going slower. It's not hit this wall, so I want to know how far it's got left to go. So I know that it's been travelling after this point for 1.5 seconds, and it's been travelling at a speed of minus 1 meter per second. So the distance it will have travelled will be equal to its velocity, so the velocity of B times the time, t1, so that's minus 1, and this will give me a displacement, so it will be in that direction, minus 1 multiplied by 1.5 seconds, so that gives me 1.5 meters, or minus 1.5 meters is my displacement in this direction. And then that means since it had 2.1 meters to go, at time t equals 1, t1, then the displacement, the distance it's still got left to hit is 2.1 minus 1.5, which is 0.6 meters. So that's how far it's got left to go. Now what I want to know is show when this happens. So imagine a couple of seconds later now, we have VA, it's collided with this container. And in the question, it tells us that it sticks to it. Now what this means is there's going to be a change of momentum because VA will exert a force onto the whole container. So since the whole container can be considered to be at rest beforehand, okay, this equation here applies, but the mass of the container is 0. So the momentum of A is going to be transferred and it's going to stick. So it's going to be, sorry, this equation, because they stick together, not this one. And then so they're going to stick together so we know work out the final speed. Now the next question on your worksheet is asking about proving that what the speed of the approach is for B, and this is a relative speed. So when it collides object A with the container, so M A V A plus MC, sorry, I should put no, V is the initial velocity in this context, but I'll just keep it like that. The initial velocity of the container is going to be equal to the mass of the A plus C and the final velocity of A plus C. So we've already said that since the velocity of the container is 0, this goes to 0. So this becomes quite straightforward. So it's going to be the mass of A multiplied by the velocity of A divided by the mass of A plus C, which is equal to 5 times 2 divided by 45 plus 5, which is 50, and that's equal to 0.2 meters per second. Now that means the container is moving in this direction with 0.2. We know that B is moving in this direction at -1. So the relative speed compared to the container is now, sorry, difference in speed is going to be, so this is the velocity of B compared to the container, right, is going to be 1.2 meters per second, because it's going -1 in that direction and the container's going in 0.2 that direction, so the difference is 1.2. So that's the difference in the speed between B and C. So now that I know that, I can work out what the time t2 is, which is when B collides with the container. So t2, we know it's got a distance of 0.6 left to travel, and we know that it is now travelling at a relative speed of 1.2. So the time is going to be displacement or distance travelled divided by velocity, and so it's 0.6 divided by 1.2, and so the time is 0.5 seconds. So I have to add that. To get t2, I have to add that 0.5 seconds. So this equation is not really finished. It should be t1 plus this quantity. So if I add that to 1.5 seconds, t2 is equal to 2 seconds. So after 2 seconds, B collides with this side of the container. Now, what will happen at this point is the momentum of B, okay, if we work out the total momentum of the container in this direction, so the momentum of A plus C is the mass and the velocity of that, of A plus C. That's going to be equal and opposite to the mass of B and the velocity of B. So if I put the numbers into this, the mass of A plus C is 50 times the velocity, which is 0.2. And the mass of B is 10, and the velocity is -1. So this is 10, this is -10 kilograms meters per second. So the momentums, because they are vectors, they will cancel each other out in opposite directions. So the end result when B collides is that the box will come back to rest again. So it will move when A hits it. When B hits it, it will stop and will go back to rest. The velocity will go back to 0. And that demonstrates why momentum is only conserved in a closed system. This system is closed within inside the box in space. So you can imagine it totally void of any other forces. So when the total momentum to start with is 0, and at the end it has to be 0, but there is this change that's gone on, there's an explosion inside the box, so they have to cancel each other out. So the total momentum, as you can see, is still going to be equal to 0. So the total momentum is conserved because it's a closed system. If I was to plot this as a displacement graph, which is what you're asked to do, then I have displacement on my y-axis and time here, and it says put numbers on. So I've got 1 second, 2 seconds, 3 seconds, 4 seconds. Well, for 1.5 seconds, the displacement of the container is 0. At this point, A collides, and so then it will travel at constant velocity up to t2, which is 2 seconds. So constant velocity on a displacement time graph is a straight line, and at that point it comes to rest again. So here, this is t2, this is t1, obviously this is t0, right? But t2 is when B is collided and then it comes to rest, so this should be a perfectly straight line again. And because the displacement is now, it will be a fixed displacement, the object's back at rest. So it's really important that you properly review momentum as a topic. The only other thing that remains to be said is remember the units. So the basic units for momentum are kilograms meters per second, but because of this equation, force times time, you can see that that can also be equal to Newton seconds. And the way that works is because if you remember, a Newton is 1 kilogram meter per second, and so the seconds cancel and you get to the same quantity. make sure you practice momentum questions properly before your exam.